Hello, my name is Patrick McClure. I'm a machine learning research scientist at the National Institute of Mental Health. And today I will be giving you an introduction to Bayesian deep neural networks for neuroimaging. Bayesian deep neural networks are a probabilistic modeling technique. Probabilistic modeling techniques attempt to learn probability distributions. Well, you might ask yourself, well, why do I care about learning probability distributions? For prediction models, if you predict just one value, you're predicting that value with 100% confidence. But in many situations, models need to be uncertain about their predictions. That is, when they make predictions, they predict multiple possible outcomes, each with their own probability. To give some sort of concrete examples of probabilistic models, we're going to look at two methods commonly used in neuroimaging. In logistic regression, the goal is to find a best fit line for a distribution of data points. This best fit line is parameterized by a weight for each input dimension and a bias. However, this best fit line gives only one predicted value for each input. In many cases, it is not reasonable to assume that a new prediction will lie directly on this line. To deal with this, linear regression often has a Gaussian noise term, or a normal noise term. These Gaussian or normal noise terms are zero mean, which means the most likely prediction is the best fit line, but points are also likely if they are close to the best fit line and become increasingly unlikely as you get further and further away from the best fit line. This makes linear regression a probabilistic model, where you have a distribution over your predictions. Another common model used in neuroimaging is logistic regression. In logistic regression, you have two distributions of points. In this case, blue points and red points. The goal in logistic regression is to find a line or a hyperplane in higher dimensions that separates these two distributions of points. For this model, just like in linear regression, you have a weight for each input dimension and a bias. However, then this weighted summation is given to a sigmoid. This sigmoid collapses the output of the weighted summation to be between 0 or 1. This value is then viewed as the probability of a particular label. The probability is a function of how close a data point is to the decision boundary. If a point is close to the decision boundary, then the model is more uncertain about its prediction. That is, the probability will be closer to 0.5. However, as a point is further and further away from the decision boundary, the model becomes more certain. That is, the probability will be closer to 1 or 0. Now, to train these models, what you do is you say, okay, we want to find the most likely setting of our parameters given our training data. What this is equivalent to is finding the best parameters that both predict your training data and are close to your prior. Often what this prior is seen as is a regularization term that prevents overfitting. In the case of these regression models, L2 regularization is equivalent to a zero mean Gaussian prior, and L1 regularization is equivalent to a zero mean Laplace prior. And so now that we have these sort of trained models, what are we doing? So we will have these parameters that we learn for the training data, and then we'll use those parameters to make predictions. However, in this setup, we are only learning one particular setting of the parameters. However, many parameter settings could potentially do well for both predicting the training data and be probable for the prior. To sort of look at that, we're going to go back to our logistic regression example. So we have our two distributions of points, and we want to find a decision boundary that separates them. So we could find one. However, there are many decision boundaries that perfectly separate these points. And the question is that which one do we use when we have a new point? And what prediction should we give? The idea behind Bayesian modeling is that we learn a distribution or a set of values for the parameters, and then take the expectation of the predictions. In this case, what happens is we would likely predict that this new purple point would be blue, because 3 out of the 5 parameter settings that we learned would give a blue prediction. However, what this also introduces the idea of something called model uncertainty. So not only do we have uncertainty from how far a point is away from the decision boundary, we also have uncertainty from the disagreement in predictions from having different probable parameter settings. To sort of see how integrating all of this information together by using Bayesian models and then averaging their predictions, we're going to go back to logistic regression. So here, what we have is we have the predicted probabilities for different points in space for a logistic regression model that was learned to separate the blue and red points shown in the figure. You can see that directly on the learned decision boundary, the predicted probability is 0.5. That is, the model is maximally uncertain. And then by looking at the darkening of the colors, you can see that as points get further and further away from the decision boundary, the model becomes more and more confident. However, this model only becomes more and more confident as you get further and further away from the decision boundary, not necessarily as you get further and further away from the training data points. However, if you do Bayesian logistic regression, that is, you learn a distribution of decision boundaries and then average the prediction of those different decision boundaries, you get uncertainties that not only get more certain as you get further away from the decision boundaries, but also get more uncertain as points in space get farther away from the training data. Now, we've sort of seen how this can be helpful in logistic regression. However, what about more complex models like deep neural networks? Let's look back at what exactly is going on in deep neural networks to sort of see how they relate to the regression models we've been looking at. So, in the regression models, let's say you have some complex high-dimensional input, such as a beta map. Then, when you do regression, what you're going to do is you're going to learn a weight for each input dimension, in this case, each voxel. And then you will learn a probability distribution for your predictions. However, by learning just one weight, you don't give the model the ability to learn interactions between voxels or higher order features unless you explicitly add them to the model. In artificial neural networks, what happens is that instead of performing regression directly on the input features, regression is performed on intermediary features that are extracted from the input. These features are generally nonlinear combinations of the features from the previous layer. In this case, since we're looking at the first artificial neural network layer, that would be the input. This sort of learned feature vector has a number of features for each artificial neuron. These artificial neurons are weighted summations with a bias, just like we saw in linear regression. Then a nonlinearity is applied. And this nonlinearity could be a sigmoid, an RALU, or several other different functions. Then regression in a one-layer neural network is performed on not the input features, but these nonlinear features computed by the artificial neural network layer. In deep neural networks, instead of performing a regression on the first artificial neural network layer, you stack these artificial neural network layers that perform the operation of creating nonlinear features of the nonlinear features of previous layers. And then, after you've performed all of the neural network layers, you'll have your last layer, which will output nonlinear features, and then regression will be performed on those. Since the last operation we're doing is performing regression, the output of these deep neural networks are often probability distributions, just like we saw in linear regression and logistic regression. Now, the question is that do the Bayesian ideas that we looked at in regression also work for deep neural networks? So we have an illustration of a deep neural network that for each parameter has a value, and then these parameter values are used to take the input to a probability distribution of predictions. In Bayesian deep neural networks, in contrast, instead of just having one value for the parameters, you have a distribution of values for each parameter. And then the question is, well, how exactly do we learn these distribution of parameters? To do so, we look at Bayes' rule, which says that the probability of your parameters given your training data is equal to the probability of your training data given your parameters times the probability of your parameters given your prior divided by the probability of your training data. This, however, can be extremely complicated and computation intensive to compute. So to apply this method for finding the probability of the parameters given you training data, approximations are often used. Two of the most common approximate Bayesian methods are Markov chain Monte Carlo, or MCMC, and variational inference. In MCMC, what happens is that you perform a random walk in parameter space to build up a point cloud distribution that approximates the true posterior. This is asymptotically exact in that if you run the random walk long enough, you'll eventually get the correct probability distribution. However, this can be extremely expensive, particularly in high dimensional spaces, such as the parameter spaces for deep neural networks. Another method that is commonly used is variational inference. In variational inference, you have a simple distribution, and you're trying to find the simple distribution that best matches the true posterior. Variational inference is often very efficient. However, because you are limiting yourself to looking at a simple distribution, there are no asymptotic guarantees when trying to model the posterior. Variational inference has been particularly successful in deep neural networks because of its ability to scale easily to models with many, many parameters. So what happens in variational Bayesian neural networks is that we have a posterior, or the probability of our parameters given our training data, and we have a simple distribution, often called a variational distribution. This is often denoted by Q. And we're trying to find the simple variational distribution that is as similar to our posterior distribution as possible. In variational inference, this is done by saying we want a distribution that is similar by using the Kullback-Leibler divergence. And so we have this divergence, and we want the divergence to be as small as possible, making the distributions as similar as possible. Then, once we have done that, we can use our trained model. What this turns out to be is that when you are minimizing your Kullback-Leibler divergence, you are minimizing the terms at the bottom of the slide. And these terms are a term that says that you need to fit the data given your variational distribution, and a term that says that that variational distribution needs to be similar to your prior. This is similar to what we saw for linear and logistic regression, in that you have one term that says you need to fit your data well, and then one term that is the regularizer that is trying to prevent overfitting. So a common variational distribution is Gaussian weights. So in Gaussian weights, instead of learning just one value for each parameter, you learn two values. You learn the mean, the most likely setting of the parameter, but also a standard deviation, or how uncertain the model is about the mean being the correct setting of that parameter. Let's say then that you have a Bayesian deep neural network where you have Gaussians for each parameter. How exactly would you make predictions? Well, we would have our distribution, and then what you would do is you would sample a parameter from its Gaussian, and you would do that for each parameter. Then you would make a prediction for the input using that particular sample. Then you would sample several different other parameters or weights. Then you would have a predicted probability for each of the sampled parameter settings. You can then average these prediction probabilities into an estimate of the overall probability of an output given an input. However, while Gaussian weights or Gaussian parameters are very common in Bayesian deep neural networks, they are not the only variational distribution that's used. One of the most popular variational distributions is based off of Bernoulli dropout. In Bernoulli dropout, you have one particular value for each weight, and then each time you run the network, for each nonlinear feature in the deep neural network, you flip a coin. And based off the flip of that coin, each neuron is either turned on or turned off. Then you run the input through the network with the neurons turned on or off, and that will give you one predicted output distribution. And just as we saw before, you could run the model multiple times, each time turn on or off different neurons. And then you can average the prediction of all these models. Another common variational distribution is Gaussian dropout, where instead of multiplying an artificial neuron by 0 or 1, i.e. turning it on or off, you instead multiply the artificial neurons by noise sampled from a Gaussian with mean 1. Meaning the most likely outcome is that the neuron will give the same output it would give if you didn't sample at all, but that because you are sampling, it won't be exactly that all the time. However, both of these methods have neuron level noise and don't learn parameter level uncertainty like you see in the Gaussian variational neural networks. So what you can do is you can combine both the Gaussian variational neural networks and the Bernoulli neural networks using something called spike and slab dropout, where you have Gaussian weights, but then you also apply dropout. And doing this fixes several of the theoretical issues of Bernoulli dropout. I won't go into that in this talk, but you can look at the references if you're interested in that. So now that we sort of have a concept of what a Bayesian deep neural network is and some of the methods used for training them, how can they be applied to neuroimaging? So to illustrate their usefulness, we're going to be looking at a case study that has applied Bayesian deep neural networks to structural brain segmentation. In this case, what you're going to have is you're going to have a structural brain image, and you're going to have an output segmentation, i.e. the structure that each voxel belongs to. What we did is we trained a convolutional neural network to take a 3D structural MRI and then output a probability distribution for each voxel over the different anatomical structures that it could belong to. In particular, we took structural volumes, then got free surface segmentations, and trained a deep neural network to predict those free surface segmentations for the training data, and then generate the probability distributions over classes, in this case structures, for each voxel for the test data. And then what you can look at is that these predictions seem very close, but there do seem to be some errors. But despite that, these methods do perform well. So what we did is we wanted to look at, do Bayesian neural networks actually help in making predictions in this setting? So we trained a standard neural network that is learning one value for each parameter. We trained the exact same architecture, except with using Bernoulli dropout. Then we also trained the same architecture with using spike and slab dropout. What we saw is that the Bayesian deep neural network with spike and slab dropout significantly outperformed the other methods, both in the inside test set, that is, test examples taken from the same data sets from which the training data was sampled, and on the out-of-site test set, that is, test examples drawn from data sets that were not used during training. When we are looking at predicted probability distributions, we not only care about the accuracy, but we also care about if the uncertainty is useful and well and good. So what we want to look at is, can we, from looking at the prediction uncertainty, find out where the network has made errors in test examples? So we can do that. we can look at the uncertainty, in this case, the entropy, or how spread out the probability mass is for each predicted probability distribution for each voxel. Then we can map that back to the inputs, or the input space, and see that often where the neural network is uncertain is where the neural network makes mistakes. To verify this, what we did is we tried to see if from a voxel's uncertainty, we could predict whether it was classified correctly or incorrectly in a test example. We found that, in fact, for all of these models, you could do that. That from just looking at the uncertainty, you could predict whether a voxel was correctly or incorrectly classified. Another use of uncertainty that we've talked about is seeing if uncertainty gets higher as you get further away from the training data. One area where this might be useful is in quality control. That is, identifying scans that have artifacts or poor quality and can't be used in downstream analyses. To see if uncertainty can be used in this setting, we took the uncertainty across the brain, averaged it into one overall uncertainty value, and then saw if we could predict whether human QC raters would say that a scan is good quality or bad quality just from that uncertainty. We did that for the various methods that we used, and for MRI QC, a popular automated neuroimaging QC method. What we found is that the spike and slab dropout significantly outperformed all the other methods, and that the Bayesian deep neural networks outperformed the non-Bayesian deep neural network. However, if we go back and look at our performance on insight and outsight, we can see that there is a large drop between insight performance and outsight performance. This is concerning if your goal is to build models that generalize to data from multiple different sites and multiple different data sets. So what we did is we tried to look at, can we develop methods for seeing if we can improve this? To illustrate that this is in fact a problem, we are going to look at deep neural networks that were each trained on different data sets to perform segmentation. We see that for insight test data, these methods perform really well. However, you see a notable drop when these neural networks are applied to data from other sites. To address this, we looked back at Bayesian neural networks, and we tried to come up with methods that could use model uncertainty to allow us to solve this issue. In particular, what this allows us to use is old neural networks as priors for new neural networks. So in this illustrative example, let's say we have one segmentation network that was trained on one data set. Then we can use that network as a prior for networks that are trained on other data sets, and then combine these networks back together in weight space, using the fact that we have probability distributions along the weights. Then this will give us a method that can then be used as a prior for additional training. To look at how this could be done, we can go back to our figures of deep neural networks. So we have a distribution, in this case a Gaussian for each weight. Then this neural network we can use as a prior, so it can influence our training of a new model. How that occurs is that you would have your Gaussian for each weight, and you can have Gaussians that are thin or have low standard deviations. That is, they are certain that the mean is a good value for the parameter, or have large standard deviations. That is, that the mean may not be the exact best value. Then, when you bring in new data, weights that were very confident in the prior, it is more difficult to change. Whereas weights that are more uncertain, it is easier for the new data to change. To see if this sort of concept works in brain segmentation, we trained a deep neural network on one data set to perform segmentation. Then we use that as a prior for deep neural networks trained on other data sets. We found that when doing so, the models generalized much better to data from different sites. Then the question is, well, we have these methods for multiple different sites. Can we bring them back together? So to do this, we can use something called distributed weight consolidation, where you have your prior, then you have your different Bayesian deep neural networks that were trained on the various sites. Then what you can do is, because each one of these is its own probability distribution, you can use probabilistic logic to figure out what is the probability distribution of their weights if you were to combine them together. Then that will give you a new network that you can then use as a prior for new data. We applied this method to the brain segmentation models that we looked at before, and we found out that it does quite well. We compared it to an ensemble. That is, we took the brain segmentation network that was trained on each of the different sites, and then we averaged their predictions for new test examples. And we found that the distributed weight consolidation actually significantly outperformed that. However, it doesn't outperform a neural network that was trained when you brought training data from all the different sites together. So this sort of indicates that when you can bring the data together, you should, but in cases that you can't, methods like DWC can be useful. In summary, we looked at how using Bayesian deep neural networks, particularly using them to add model uncertainty into the overall uncertainty of our models, can improve prediction uncertainty. We saw how this improved prediction uncertainty can lead to better prediction of errors in test examples and prediction of data quality, particularly in the case of QC of anatomical neuroimaging scans. We also looked how using model uncertainty can enable using old neural networks as priors to help build more general deep neural network models. I want to thank all of my colleagues and collaborators who basically made this work possible. Thank you for your time.